So I wake up at 12 a.m. and I just cannot fall back asleep. So I think to myself, well, how about I do some math? This question says we need to find the area of the region bounded by the curves x equals y minus 2 raised to the second power over 3 and y equals 8 minus x. Okay, so we have two equations here and we need to find the area of the region that's bound in between them. Well, let's use Roman numerals and I'll say that this one's equation 1 and that this one's equation 2. It's just something about Roman numerals, they're just classy. Okay, so I got these two equations here. Now just note the different orientation of x equals y minus 2 squared over 3. See, because I wrote it out as x equals 1/3 times y minus 2 squared. Okay, but let's just take a look at these two equations here and let's just try to like think in our heads what could be going on here. How might this look graphically? Okay, so do you see how equation 2 is raised to the second degree? It's being raised to the power of 2, and that means that it's going to be a sideways parabola. Okay, and then you see equation 2, y equals 8 minus x. It's being raised to the degree of 1, so that just means that it's going to be a line, it's linear. Alright, so if you put these two equations together on a graph, it should look something like this. It's not perfect, but it's gonna look something like this here in the square. And then in here, this is gonna be the region in question, and I'm shading in here in blue. All right, so what's up with this? What do we need to do? Well, we need to find the points of intersection. How are we to find the points of intersection? We need to set the values equal to each other. We're going to take these two equations up here, and we're going to set them equal to each other. Just take a look and see the relationship between these two separate equations and this one combined equation here. On the left side, there's a fraction. Let's clear out the fraction and get everything to one side. So we could do that by multiplying the left side by 3, which of course means that we need to multiply the right side by 3. And then we'll find that these 3 on the left side, they cancel. 3 times 8 is 24. And then 3 times y will be 3y. Let's investigate this y minus 2 squared. It should look familiar. Y minus 2 squared is the same thing as a minus b squared, so we need to apply this formula. So at this point, what we should have is y squared minus 4y plus 4 equals 24 minus 3y. Now I'll make some space. We're going to continue to try to get everything to one side. What we can do is add 3y to both sides. Now we have y squared minus y plus 4 equals 24, and we're going to subtract 24 from both sides. At this point, we have y squared minus y minus 20 equals 0. This trinomial has a leading coefficient of 1, so we need to find two numbers that multiply to negative 20 but then add to become 1. What are the factors of negative 20? Negative 4 and 5. Oh, but that's going to be positive 1, so then we could do positive 4, negative 5, and then that will add to be negative 1. So then to factor this here, we'll say that y minus 5 times y plus 4 equals 0. So we have two separate binomials here that are both set to 0. So y minus 5 equals 0. If we add 5 to both sides, then we'll find that y equals 5. And then y plus 4, if we set that equal to 0 and we subtract 4 from both sides, we'll find that y also can equal negative 4. All right, now let me go ahead and make some room. Bring this up. Now that we've found y to be equal to 5 and negative 4, we can move forward with finding the points of intersection. But what does that even mean? What does it mean when I say let's find the points of intersection? It means that we want to find the points in which these two lines, the parabola and the line, meet. Where do they cross over? So a point of intersection, for example, would be right here, and the other point of intersection would be right here. Since y is equal to 5 and -4, what we're going to do is we're actually going to plug 5 into the linear equation, and we're also going to plug -4 into the linear equation. Let's start by plugging in 5 into the linear equation. Let me remind you that the linear equation is 8 minus x. So what we'll do is we're going to plug 5 in for x. So this will become y equals 8 minus 5. We'll find that this is going to equal 3. So what does that mean? That means that the first point of intersection is going to be 3 because that's what we found the equation to equate out to be, and 5 because that's what we originally plugged into the equation. Next, we're going to plug in -4 to the equation. So we're going to have y equals 8 minus -4, which is really just 8 plus 4, and that's going to equal 12. Now, so what that means is the other point is going to be 12, -4. At this time, I'd like to analyze the parabolic function now that we've already have our point of intersection. A parabolic function will always be of the form x equals a times y minus k squared plus h. Now this makes sense because if we look at our parabolic function, we'll find that a equals 1/3, k equals 2, and h equals 0. Now you might say, Stella, where is the h? The h is hidden. It's secretly just plus 0. It's not really a secret, but you just can't see it. um, Next, we'll find the vertex. When you have an equation of this form, right, and it's parabolic, the vertex is always going to be h and k. So what does that mean for us? That means that the vertex is going to be 0 and 2. So that's what's up with our parabolic function. I'm going to make some space. What we'll do now is we're going to take this information and we're going to use it to put on for a graph. We even have a rough idea of what the graph is going to look like. Let's bring our attention over to the points of intersection. Let's look at 3 and 5. Along the x-axis, we're going to count 1, 2, 3. Along the y-axis, we're going to count 1, 2, 3, 4, 5. Right here will be our first point of intersection, where the line goes through the parabola. Next, we'll do 12 and 4. We're going to count out 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then we're going to count down 4. 1, 2, 3, 4. This will be our second point of intersection. All right, now let's connect the dots here because this is our line. Go ahead and do me a favor and just pretend that this is a straight line. We can even label it. This is y equals 8 minus x. This graph is not drawn to scale, by the way. Let's look at the parabolic function. The parabola will be blue. Now we know the vertex is going to be 0, 2. We're going to go to the origin here. We're going to say that x is 0, and then we're going to count up 2 because y is 2. 1 and 2. Put a dot right here. This is the vertex, which means the parabola is going to expand outward and cross over the line right here. And right here. Now, it's not perfect, but it's what I got. I'm going to hit it with a label. Now remember, we're being asked to find the area of the region bounded by the curves. The region bounded by the curves is right here. You see what I'm saying? In order to find the area of the region bounded by the curves, we need to set up a definite integral. But in order to set up a definite integral, we need to know whether or not we're integrating with respect to x or with respect to y. To determine whether or not you're integrating with respect to x or with respect to y, you need to look at the vertex of the graph that you just sketched. To help us understand if we're going to integrate with respect to x or respect to y, we're going to draw a slice. But in order to draw a slice, we want to take a look at the orientation of the parabola with respect to the line. See how it's horizontal? That means if we were to draw a slice, it would be horizontal, and it would look like this here in red. A horizontal slice always means that you're going to integrate with respect to y. Now, if this were to be rotated 90 degrees, that means that it would be a vertical slice, and you would integrate with respect to x. But because the orientation of the line and parabola are of such, it's a horizontal slice, thus we will integrate with respect to y. Written before you is a formula that shows you how to find the area of a region bounded by curves using a definite integral. It says that the area is equal to the definite integral from a to b of f of y minus g of y. Now watch my cursor. This dy at the end means that we're integrating with respect to y. Let us use this formula to set up our integral. We're working with a definite integral here. We need to find the lower bound of integration and the upper bound of integration. To do this, please bring your attention to the points of intersection. Here we have 3 and 5. This 3 is x. This 5 is y. Likewise, this 12 is x. This negative 4 is y. How can we find the lower bound of integration? The lower bound of integration is going to be the value that is lowest for y. Or if you'd like to interpret it graphically, you can see that negative 4 is right here, and that is going to be our lowest point. Therefore, the lower bound of integration is negative 4. The upper bound of integration, or the highest y, is going to be 5. So we'll put 5 for b. For f of y, we're going to plug in 8 minus y. Then we're going to subtract. What are we subtracting? G of y. For g of y, we'll plug in 1/3 times y minus 2 squared. Remember, we're integrating with respect to y. This here is the setup of our integral. So now we can integrate. First, what I'll do is I'll expand y minus 2 raised to the second power. We will integrate further by distributing 1/3 to this trinomial within the integrand. Alright, I'm gonna grab some room. Okay, so at this point, I'm gonna take this here and I'm gonna make more room around it because I want to be very thorough with how to go forth with this. Basically, to simplify what's in the integrand, we need to take this and we need to break up the 8 and the negative y, and we're going to distribute them according to the like terms. Like, we're not going to distribute in the multiplication sense, but we're going to line them up with what is similar. It's best to have the highest degree variable at the beginning. Allow me to elucidate further on this. You see this y here? This is the same thing as 3/3 y. That's the same thing as 1y. Remember, every constant has an imaginary 1 underneath it, but we can't just add these two together. We can't do that because they need to have a similar denominator, or a common denominator rather. So we can do that by multiplying the bottom by 3 and multiplying the top by 3. Now what we'll do is we'll integrate term by term. I'm going to make some space because we're going to thoroughly integrate. What I'm going to write out next is called the constant multiple rule for integration. Okay, this is the constant multiple rule for integration. What I'm going to write below that is going to be the power rule for integration. This is the power rule for integration. There's one more rule that we need to write out in order to tackle what's in the integrin. It's called the constant rule for integration. This is the constant rule for integration. Okay, let's integrate term by term. So the first term is negative 1/3 y squared. Via the constant multiple rule for integration, the negative 1/3 comes outside of the integral. So really, we're just taking the integral of y squared. Now, to take the integral of y squared, please bring your attention to the power rule for integration beneath the constant multiple rule for integration. So basically, what we need to do is we need to have y brought up to the power of 2 plus 1 over 2 plus 1. Because if you plug it into the power rule for integration, the 2 is the n and the y is the x. So what that means is we're going to have y cubed over 3, which is the same thing as 1 over 3 y cubed. But then we need to multiply 1 over 3 to negative 1/3. And so the result of that is going to be negative 1/9 y cubed. And now we'll do the second term, 1/3 y. So it's going to be a similar process as the first term, because what we'll be doing is we're going to take out the constant, which in this case is 1/3, and then we're going to take the integral of y, and y is being raised to the first power. So if we set y equal to x and then 1 equal to n, we'll find that we have y squared over 2. Then we need to multiply back that 1/3. So y squared over 2 is the same thing as 1/2 y squared. Then we'll multiply 1/3 and we'll find that we're going to get 1/2 y squared times the original constant that we pulled out, which is 1/3. The answer will be 1 over 6 y squared. So now at this point, 20 over 3 is a constant, which means that we're going to have plus 20 over 3y. And then since this is a definite integral, we're going to have our evaluation bar, and it will read the lower bound of integration as -4 and the upper bound of integration as 5. See, now we can evaluate it via the fundamental theorem of calculus. This is what the equation will look like when we evaluate it via the fundamental theorem of calculus. Now this is the full setup. Now if you evaluate this entire equation, you're going to get 81 over 2. Thus, the area of the region that's bounded between the curves is going to be 81 over 2. That's our answer. Thank you so much for watching. Glory to God.